Hello, welcome to the continuation of our SPI free lectures. My name again is Negedu Godwin. So we continue from where we stopped last time. We're looking at wave parameters and sound wave itself. So there are many types of waves. We have sound waves, we have sine waves, we have radio waves, light waves, waves on the surface of the sea, contraction waves in the myometron, crowds making wave in football pitch, electromagnetic radiation travel as transverse wave. Now, sound wave is a sine wave which travels as longitudinal wave, in which the displacement of the particles is in the same direction that is parallel to the wave energy. But I want to quickly remind you from the first video that sound is a form of energy. It's longitudinal wave. It's also a mechanical wave. It's a type of pressure wave that is able to converge and diverge. This particular property, you will see it in the paid class, how it applies to your probe. Sound is able to reflect. It's not a transverse wave. It's not ionizing radiation, so do not be afraid. It's not electromagnetic wave. So let's look at some very interesting things. Acoustic variable. You see, sound is a form of energy which propagates through matter in some form of mechanical and longitudinal wave. Waves carry energy, not matter, from one point to another. A wave is a traveling cyclic variation of acoustic variables. Acoustic variables are measurable quantities that vary within a medium as sound propagates through the medium. We need to know 4 acoustic variables that exist. You have the pressure, density, particle motion, and temperature. As the sound wave propagates through a medium in cyclical fashion, each of the above acoustic variable varies and could be measured in medium. For example, the pressure in the medium will alternately increase and decrease with the vibration of the molecule. Remember, pressure is the amount of force in a given mass. The unit of pressure is Pascal. Other units are pounds per square inch, Newton per square meter. Density is the mass per unit volume. Unit of density are kg per meter square, gram per centimeter square, and pounds per feet cube. And temperature is the concentration of heat energy. The units are degree, Fahrenheit, Celsius, and Kelvin scale. Now, particle motion is the distance moved by a molecule in the medium. The unit is a unit of distance, typically the nanometer. The most widely used acoustic variable are pressure and density. Your fluctuation in the two variables will be used to describe the concepts of sound waves. Sound is a propagating wave which results in cyclical changes in resting pressure of a medium. Resting refers to the state of the medium when there is no sound traveling in the medium. The cyclical variation of pressure may be plotted graphically as sine wave as depicted in the following diagram. So from this diagram you can see the direction of propagation from left to right, and you also notice the areas of compression and the areas of refraction. The amplitude, of course, is the height of the wave, and you notice the cycle. This end from here to here makes one cycle. Then this is the wavelength here. Regions of high pressure are accompanied by regions of increased density. This high pressure, high density region in a medium carrying a sound are known as compressions, that's condensation. That's where all the molecule particles come together. At that point, it's dense. There's a condensation going on there. Conversely, the region of low pressure are accompanied by areas of decreased density in the medium. This low pressure, low density region are known as refraction, as relaxation. As can be seen, the pressure is continually changing and reach a high in one direction, that is at the maximum point, and then a low point in the opposite direction as minimum. The amplitude of the wave is measured on a vertical axis. It is the difference between the maximum and the resting value. The amplitude of a sound wave is its strength. In audible sound, the amplitude of the sound is its loudness. That is when it's applied to your speakers. So the amplitude will be the loudness of the speaker. That's how you can relate with it with respect to your speakers. Now, sound wave parameters. Sound wave is a longitudinal wave which can be drawn in the form of sine wave. One wave cycle is composed of one compression and one refraction. Now, you need to remember this diagram. One cycle composed of one refraction, that is realization point, and one condensation point. That's what makes one full cycle. In areas of compression, the particles in the medium are squeezed together, resulting in an increased pressure and density. In areas of refraction, the particles are drawn apart, resulting in decreased pressure and density. Thus, the pressure distribution changes as the sound wave travels through the medium. The areas of compression have positive elevation, and the areas of refraction have negative deflection in the cycle. A sound wave can be described by the following parameters: frequency, period, wavelength, power, intensity, amplitude, and its velocity, that is the propagation speed. So let's look at these parameters one after the other, and it's important we know them so that we can now understand how it's applied in our ultrasound machine in producing diagnostic images. Frequency is the number of cycles per second. It is the number of vibrations per second. It is the number of times in a second the piezoelectric crystal vibrates, that is, expand and contract. So if you look at the frequency, we cannot overemphasize on that. It's just the amount of cycles per second. So this is the unit for frequency, which is hertz. Hertz is 1 cycle per second. In medical diagnostic ultrasound, the effective transducer frequency range is 2 MHz to 12 MHz, commercially available today for clinical practice. In clinical practice, the effective transducer frequency range is governed by depth, size, and attenuation coefficient of the area of interest. The choice of transducer frequency used in diagnostic ultrasound is limited by two factors. It's very important you know this, because we're now beginning to dive into what image optimization would mean in practice. So your choice of frequency, transducer frequency, is dependent on two major limiting factors. The first is tissue penetration, image depth. How deep do you want to go will determine the choice of frequency. And the second is the resolution, the image quality. How much of resolution do you want? What's the quality of image you want? That is the spatial resolution. So you need to know that higher frequency is better the spatial resolution. If you have higher frequency, your spatial resolution is better, but you will not get to penetrate deeper tissues. So in general, the more superficial and less attenuating the structure, the higher the frequency is used, and vice versa. So you want to access superficial tissues, use a very high frequency, because there will not be much depth, but the resolution is very high. The best images are generally produced with highest frequency transducers. The ability to detect small structures or superficial structures improves with higher frequency. When selecting a transducer for ultrasound examination, the highest frequency transducers, which can see through the area of interest, should be used. So it's a trade-off. What will produce for you, or rather which frequency of your transducer will produce for you the required depth and required quality for your area of interest. You need to know that the relationship of frequency with image quality is very key. So axial resolution here is directly proportional to the frequency. If the frequency increases, axial resolution improves. Thus, the higher the frequency, the better the image quality. Why does penetration decrease with increasing frequency? It's all due to attenuation. So you remember, attenuation means gradual weakening. So there's a gradual loss of strength of your sound wave as it goes deeper. So it is defined as a gradual reduction in amplitude and intensity, which is strength, of the incidental ultrasound wave as it travels through the tissues. Attenuation occurs through three processes. 80% of the sound is absorbed, the sound is reflected, and sounds are scattered, refracted. So this 80% of sound beam gets absorbed and it passes through the tissue. As it passes through the tissue, as attenuation in a structure increases, the depth of penetration decreases correspondingly. As frequency increases, so does attenuation increase. You need to understand that. So the deeper you go, you require increased frequency. but there is a weakening as you go deeper. There's a weakening of the sound wave. However, the relationship is not exactly linear but variable depending on the type of attenuation process that occur in the medium. So, as a rule of thumb, use the highest frequency that will penetrate to the depths of interest. Higher frequencies are preferred but have limited penetration. Lower frequencies gives poorer resolution but can penetrate more than high frequency. So when you understand that, your choice of transducer or probe during your scan will be quick to determine. Of course, I know that there are people who strictly just use a curvilinear probe in almost all the area of interest. Well, that comes with a lot of limitations, and it's better for you when you are experienced in the skill, but I will not advise you do that. If you have the facility, please make sure you use the correct probe for the correct areas of interest. So the optimal choice of frequency of transducer for a diagnostic ultrasound study is a compromise between the need to penetrate the area of interest and the need to adequately display details, that is your image quality. So let's look at this diagram. It is typical for frequency range for your diagnostic ultrasound. So generally, when you do abdominal, you basically will use 2 to 5 megahertz. You are trying to access the gallbladder, 3 to 5 megahertz. OBS and gynae, it can vary between 3 to 7.5 megahertz. Thyroid, OBS and gynae, of course, you know, we're talking about early pregnancy to term. Thyroid, breast, scrotum, you can vary your transducer frequency from 5 to 12 megahertz. Adult heart, if you are doing a cardiac examination, 2 to 3 megahertz. Pediatric heart, you can use 3 to 5 megahertz. Of course, you know, the chest of an adult is more bulky than that of children, so you understand the trade-off between the depth and quality here. For eye, ocular scan, 7 to 15 megahertz, and endoluminal ultrasound is 15 to 30 megahertz. That's for choice, making a discrete choice for your ultrasound transducer with respect to your area of interest. Period. This is the time it takes for a sound wave to complete one cycle. It is the length of time to complete one cycle, just a single condensation and relaxation of sound wave in one per time. So the equation of period is basically inverse frequency. The unit of period is millisecond or microsecond. It's typically expressed in microsecond because microsecond is reciprocal unit of megahertz. So at 5 megahertz, the inverse will be 0.2 microsecond. I hope that is clear. Relation of period with frequency. Period is the reciprocal of frequency, like I've said. An increase in frequency means decrease in period. So the inverse proportionality. An increase in period means decrease in frequency. If frequency is constant, then period can not change. So clinically, the frequency of sound of sound wave is very important, but period is not. However, period is useful to understand pulse, ultrasound, and bio effect. We have a class on bio effect, and you understand that. So wavelength is the distance a wave travels to complete a single cycle. It is expressed as lambda, as a Greek letter lambda. The unit of wavelength is meter, centimeter, millimeter. It can be measured between two corresponding identical points on the wave. If the distance between two corresponding points on the wave is close together, then the wave will have a short wavelength. Of course, if they are farther apart, the wave will have a longer wavelength. So wavelength depends on two factors: speed and frequency. If either of these change, the wavelength will change. So that is direct proportionality. This relationship is also known as wave equation. So please keep this in mind, because if you're writing your ARDMS certification exam, you are definitely you're coming across this in SPI. So velocity is equals to frequency times lambda, because they are proportional. True. As can be seen from the equation above, wavelength is directly proportional to velocity of sound and inversely proportional to sound frequency. Wave with high velocity have wavelengths and they have longer wavelengths, and waves with high frequency have shorter wavelengths. The wave equation is the fundamental relationship that must be known. You use it to calculate wavelength. Now, do not use it to calculate speed or frequency. In clinical ultrasound, velocity of sound is taken as constant in soft tissue. That's why you cannot use it to calculate speed or frequency. I hope this is clear. Underline this and take note of it seriously when you face an exam. So this is an example to calculate wavelength. Once you know the velocity of sound, which is constant for tissues, you know the frequency, then the wavelength is known. As simple as that. And you use to calculate the wavelength. So what is the clinical significance or importance of wavelength? You know, the sonologist rarely thinks directly about wavelength while operating the ultrasound system. He or she thinks about transducer frequency and also about the focus. However, each time the transducer is changed, the wavelength by necessity will also change. Wavelength affects the pulse length, which is a direct measure of the axial resolution. Therefore, from a clinical perspective, shorter wavelength means shorter the pulse length. Shorter pulse length means higher axial resolution, thus the better image quality. That is, higher frequency give you better image quality. Shorter pulse length. And shorter wavelength. So with this, I believe it has driven home some of the parameters necessary, in fact the fundamental parameters necessary for sound wave. And in the next video we'll move into how the velocity and propagation speed of sound. So keep a tab, we'll continue from here. Thank you.